I want to remind you first that the force on a charged particle moving through a magnetic field is equivalent to QV cross B. And the direction of that force is based on the right-hand rule. And you guys had a lot of fun flipping each other off. There's nothing more fun than a day of showing off the right-hand rule, especially with those nails. It's like you really mean it. Well, if we were to look at the magnitude only and ignore for a moment that the sine function would be a part of this, and we can include the sine function, but I'm just looking at units for a minute. The unit for the magnetic field would have to work out to be in terms of force, charge, and velocity, which makes for an odd unit, newtons over Coulomb times meters per second, which Newton times second over meter Coulomb. None of these are great, but both of them has been assigned to the Tesla. The Tesla is the unit of measure for a magnetic field. Unfortunately, or fortunately, no matter how you want to look at this, it's based on a Coulomb. So just like in similar cases where an amp is also based on the Coulomb and an amp is a very large measure of current, Tesla is a large measure of magnetic field. So because of that, a 1 Tesla field can actually begin to be pretty dangerous. 2, 3 Tesla fields can move stuff around the classroom. Not because you want it to, but because it grabs trash cans and moves it around the room.
I thought that magnetic fields couldn't move things from rest.
They can't deflect a charge, they can't speed up a charged particle from rest or stop a charged particle. You have to understand, I'm very careful about choosing my words there. So a magnetic field cannot set a charged particle into motion, but a trash can doesn't get picked up and moved because it's a charged particle. Part of what we're missing here is the nature of how paramagnetism works. Now, I've left a word out because we've yet to generate any information about where magnetic fields come from. We started this discussion with the concept that magnetic fields exist, and this is how they affect charged particles. What we have to do, and we're not going to do it today either, is develop where the magnetic field comes from. Now, it shouldn't be hard to put the symmetry in place. For example, hold on. If we look at the symmetry for the electric field, a charged particle at rest creates an electric field. An electric field pushes on charged particles. There's symmetry, right? A force is experienced by a moving charged particle in a magnetic field. How do you think a magnetic field is likely created if we apply the same symmetry? Or do you want me to go back through that again? A charged particle at rest will experience a force in an electric field. An electric field is created by a charged particle when at rest. A moving charged particle will experience a force in a magnetic field.
So magnetic field is caused by a moving charged particle?
That's it. So we will develop over the next couple of days, not today, the concept of how a magnetic field is created by the motion of a charged particle. Now, here's the weird part, and the part that will make this more challenging. Just because the particle is moving doesn't mean it stops producing an electric field. The electric field is still there too, but the electric field is changing location because the charged particle is moving. But now, because of the motion of the particle, it's also creating a magnetic field. Both fields are created by the particle when it's moving. Okay? So we'll come back to that. Right now, there's a few other things we need to look at before we go on. And the first is we have charge and velocity attached to this. Where else has charge and velocity been kind of connected together? Do you guys remember? How about I help? since you got the confused look on your face, and I don't want you to be confused. But before I do, velocity can be expressed as a derivative, right? I could rewrite it like this, right? Now, this is not a v, this is dx there, dx dt. Now, we would get the same units if this was dq dt times x cross b. Do you see that? That the units would end up being the same. I'm not saying that these are the same equation. I'm saying that the units of the result would be the same. I bring that up because this is a representation for current, the flow of charged particles. And it shouldn't be a surprise to you guys that a current would have within it lots of moving charges, and they should experience a force due to a magnetic field. This expression suggests that a current-carrying wire would experience a force if we were to place it inside a magnetic field. You follow where I'm going with this? Yes or no? Yeah? Well, let's consider that in a wire that's experiencing a current. If a current's passing through a wire, if we consider a conventional current for just a minute, the idea that a conventional current is a flow of positive charged particles. If I were to surround the area around a wire with a magnetic field, then inside the wire, we could conceive the concept of positive charges flowing in the wire, all of them experiencing a force due to the magnetic field. Using the right-hand rule, a single charge would be moving upwards towards the top of the board. The magnetic field is into the board. Each charge should experience a force to the left. Does that make sense? Yeah. Now, here's one important difference between free charges and a current. When these charges experience that force, they are not free to move in any direction. They are trapped inside the wire, which means although they might all drift to the left, they're not going to all of a sudden start traveling in a circle. They're going to press on the wire and push the wire to the left. Now, if you're concerned that we know that these aren't positive charges, these are actually negative charges, then how can that still work? Could we test this? Would this be a way of testing whether it's positive or negative charges in the wire? Consider that if the current is upwards, then that suggests a negative charged particle is moving down through the wire. Right? If that's real flow of charged particles, using the right-hand rule, we'll still find that the negative charges are also pushed to the left and provide the same result. So we can't use this to determine whether it's positive or negative charges moving in the wire, but we get the same result no matter what, that this wire is going to experience a force to the left due to the current passing through the wire. Yeah, because negatives are pushed in the opposite direction that the right-hand rule gives.
So you use your left hand?
You could use your left hand and call negative charges the left-hand rule. But be careful when you do that.
Oh, okay, that makes sense.
Yeah, okay. Just be careful when you're using your left hand, because if that makes sense to you, that's great. But everything in physics is based on the right-hand rule. Let me point out an example where that could get you into trouble. In electricity, you're right, the left-hand rule would work for negative charges. But other things that use the right-hand rule, like torque, don't have a negative like that. There's no negative mass, and torque is based on the inertia of the mass. This is based on the charge of the particle, but force is based on inertia of the mass. So you would never use your left hand in calculating a torque, even if it would be more convenient to arrange your hand to do so. So I caution you in using the left-hand rule to make sure you understand that only works because of negative charges doing the opposite of what a positive charge would do. So, getting back to this, a current-carrying wire will experience a magnetic force, and the magnetic force that the wire experiences is equal to I L cross B. We're going to use a capital letter L here and not the X, and I want to definitely cover why we use an L. The L represents the amount of wire or length of wire within the magnetic field. So first and foremost, this magnetic field only acts on the portion of the wire that's within it. Any part that's outside the magnetic field doesn't get pushed around by the magnetic field. But also, notice the bar above the L? We use the direction of the wire in calculating the direction of the force from the magnetic field. That should make sense that the wire's arrangement in the magnetic field would be the part that would choose the direction of that force. So the capital L here is to indicate the length of wire in the magnetic field and its direction. Okay so far? Now, this might not have been obvious, but this represents something that is the start of how electronics truly can start changing the nature of the human experience. Because if we have a current-carrying wire and we place a current through that wire and we suspend that wire in an area that has a magnetic field, this means the force on that wire is directly proportional to how much current is running in that wire. If you don't understand the implications of that, consider that we now have a direct method to get mechanical energy from an electrical system. In our prior example, we couldn't start a charged particle moving with a magnetic field. And we can't here either. If I have just a current-carrying wire sitting in a magnetic field, it will not start moving on its own. But if I place an electric field through the wire and electrify it, and a current begins to flow, then by switching on the current, the wire will experience a force immediately. And that force will act to push the wire around. This means we have an electrically controlled method for causing physical work to be done. I flip a switch, turn on a current, the wire gets pushed to the left. Now, can you think of anything else that does that, where you flip a switch and it starts to move? Like every electric motor in the world. Yeah, but you know, it's amazing, you might not put this together, but up until this time, if you want to do physical work using physics, you were looking at having either to deal with an expansion of a gas by heating it, so steam engines, gasoline engines, but a snap-on electric motor meant that you could instantaneously begin to move something using electricity. And people were wondering what good was electricity besides lights? And in the beginning, all they saw was a replacement for gas lights. You get the tungsten to heat up and make it light up. We could have snap-on electric lights in our house. We didn't have to go around lighting kerosene, which, by the way, was one of the leading causes of house fires, was kerosene lamps falling, breaking, or in some other way causing a house fire. The concept of snap-on electric lights was very appealing because it meant that you had a safer alternative. You didn't have to always go out and get kerosene. You could have electricity delivered to your house. And you had lights you could flip on with a switch, as opposed to having to walk around with a candle or some other wick to get something lit. But what this was causing, this was allowing us to do physical work using an electric motor or a magnetic field. You need a couple of permanent magnets, which we had been creating or digging up from the earth for years. The original lodestones, which are just pieces of iron that have been frozen in the Earth's magnetic field, had a permanent magnetic field associated with them. You could create an electric motor if you could put a couple of permanent magnets around some loops of wire. With those loops of wire, they would be pushed around by turning on a current. All of a sudden, we have a method for manipulating objects using current. This revolutionized all of the 20th century, the concept of doing physical work with an electrical system. It meant that we had a new use for electricity, well beyond the concept of just turning on lights. I mean, there were electric cars before there were gasoline cars, because the electric motor was created about the same time as the gasoline motor. But there was no easy way to package up the electricity because there weren't battery manufacturers at the time that were sophisticated enough to put together the whole package. However, what really revolutionized the automobile industry was the ability to turn a key and get the car to start. Before that, you had to be strong enough to start the car yourself by turning it with a hand crank, which meant you had to take a big crowbar, put it in the front of your car, and turn it to get your car started. That's how people started cars in the 10s and 20s. So all those Model Ts came with a big crowbar-looking thing that got shoved in the front of the engine, and you cranked it over to get it started. If you weren't strong enough, you didn't drive. Now, with the invention of the electric starter in a car, cars all of a sudden could have electric lights because they already had to have a battery there to start the car, and could be started with the turn of a key, making the possibility of driving in everybody's reach. At this point, most things that you utilize in your life that do physical work do so with an electrical system. And it all comes down to the fact that a wire can experience a force, a full-on force inside a magnetic field. All we need to do now is build the final piece, which is how do you generate a magnetic field? And we probably could change the world. That's exactly what happened in the 1910s, is we had enough information now to generate the possibility of a small, compact electric motor. How many of your children's toys have had electric motors in them? Every one of them that moves, that has batteries.
I don't have children. Anyone?
Okay. Clearly, you I used possessive there differently than you did. Not your children's toys, but your children's toys. You had toys, children's toys.
Why didn't you just say toys?
All right, you're right. Why did I just say toys?
We were talking about adult toys.
One thing we have to take a few moments to cover is something called the Hall effect. No. The Hall effect is the experiment that determines the charge of the charge-carrying particles in a current. So it's an important experiment, and it's interesting, to say the least. The concept of the Hall experiment is pretty easy to understand, but the result of the Hall experiment is what is kind of interesting. The idea put forth by Hall was that if we had a flat wire, so this is not like a wire that splits, but a flattened piece of metallic wire. And we connected it to an EMF. That generates a current, say, in this direction. then in this flattened piece of metal, if the current carrying pieces are positive, there should be a positive charge particle with a drift velocity in this direction. Does that make sense? Any question about that? All right. So, by flattening out the wire, the charges would have more spaces to move. So if I was to then take this and apply a magnetic field in the region of the flattened piece of wire, the positive charged particles would experience a force, in this case, to the right. You should prove that to yourself just so you are on the same page as me. But they would experience a force in that direction. Are we agreed? Remember, you can always turn your paper to help you with this, or you can try and contort your body. More fun to me to watch. Now, this is going to cause the charges to drift to the right side of the bar. Now remember, if the positive charges are the things that are moving, the right side of the bar is going to become positively charged as more of the positive particles drift towards the right side, and the left side of the bar is going to become negatively charged. This means we should be able to measure a potential difference across the width of the bar, with the right side being the high potential side. Does that make sense? Any questions about that? So, I'm just going to write this rule out. If the charge carriers are positive, the right side of the bar will be the high potential. You just measure with the voltmeter, see if it is. Now, we've seen an example where we get the same result, whether it's positive or negative charge. So let's try this test with a negative charge. Oh, I didn't want to do that. All right, so let's consider reestablishing our line of reasoning. But this time, let's consider doing it for a negative particle. So I'm going to have the same magnetic field. Still going to use the magnetic field into the board, because what I'd like to have is an experiment we could actually conduct to figure out what's moving inside the wire. So I want to keep everything I can the same. The conventional current will be traveling the same direction. The magnetic field will be in the same direction. But we know that with the conventional current in this direction, negative charges would actually have a drift velocity in this direction. Now, applying the right-hand rule, these particles will also experience a force to the right. So these particles will drift to the right. They'll experience a force in this direction, worst arrow ever. It's a sucky arrow. In fact, I'm so embarrassed by that, I have to redraw it because I want my viewers in Uganda to think that's how an arrow looks like. I know, I'm disappointed. But every once in a while I gotta throw a Ugandan idea out there, and just in case they start picking it back up. Now this means, of course, that the charged particles are going to travel to the right as well. Now, the result of this will be that the right side of the bar will now become negatively charged. And this will reveal positive charges on the left side of the bar, which provides us with a definitive test. If the charge carriers are negative, the left side would be the high potential. So you conduct this experiment, and you can probably guess what happens. By conducting this experiment, you find that the charge carriers are negative. The result of all of this is the Hall effect, as an experiment, can determine the charge of the charge-carrying particles in a current. It provides definitive proof that that the charge carriers are negative. It does not provide proof that they're electrons. It provides proof that they're negative. But we haven't done the math portion of this. The math portion of this will show that we can solve for the charge-to-mass ratio, which you know is a signature of the value of a charge and its mass, would tell us whether it's an electron or a proton. So we'll cover the rest of this tomorrow.